Alright, so I was on a bit of a soapbox tirade rampage there. I apologize, but I really need you guys to understand. It's real easy to go pull an equation off the internet that is going to kill people if you use it incorrectly. Literally in our line of work, you use an equation in the wrong situation, you can kill people. That's the reason I really try to pound it into you guys. Don't just use some quote-unquote expert on Chegg's opinion, because you don't know their credentials. You may know more about the subject than they do. Keep that in mind. And I don't know what the vetting process is, but I don't think it's real in-depth. I think they're happy to take your money. Anyway, like I said, let me get off my soapbox. Let's continue on. Okay, this is the third way you could solve that last problem if you want to. Now, so what I want to also talk about today is let's work our way up to the third law of thermodynamics. And then I do have an example problem. We may not solve it, but let's at least set the last example problem up. I'm going to make sure I don't have a lot of glare on this. I do have a glare from my light. Let's see if I can move this down. There we go. Okay. So, the rest of this lecture then, we talk about conceptually what is entropy. Now, we've mentioned this a little bit before. We said entropy is a measure of disorder, a measure of chaos, a measure of randomness. This entropy, the total entropy of a substance, is equal to, now this is not, right, this is not your specific heat ratio. This K, I believe this is the Boltzmann constant. It's a different constant, but this is not K equal to C sub P over C sub B. This is a different K. Okay, like I said, I think this is the Boltzmann constant. Go look that up. If you find information, feel free to share it in the comments there. But this constant times the natural log of what we call the thermodynamic probability. That's a value that ranges from 0 to 1. That measures our ability to predict exactly what a molecule is doing or what something, a particle, is doing at any given time. So if you think about, say, you know, you guys know me, I always have some kind of liquid in a cup, and this is just water, not vodka there. I just got water here to keep me hydrated so I don't lose my voice. Now, we know where these molecules are. They're right in there. They're not going anywhere. Well, some of them are actually vaporizing and coming out, but not too many, very few. If I just let it sit there, those aren't moving too much. We have a pretty good idea where those water molecules are right now. Very low, very high thermodynamic probability. Our ability to predict exactly where those molecules are and what they're doing is pretty high. It's really high if I had some ice. It's really high that we can predict exactly where an individual water molecule is in a cube of ice and exactly what it's doing. It's not doing much. It's just stationary. So as a substance becomes solid, the molecules become very predictable and our thermodynamic probability becomes very high, meaning the entropy becomes very low. What is the natural log of 1? Pause and go figure that out if you need to. Take the natural log of 1. Take the limits here. Natural log of 1, what is that? And the natural log of 0, what is that? And what does that tell you about the entropy? Right? So again, as our thermodynamic probability increases, basically the entropy decreases. So if I've got 100% thermodynamic probability, that tells us something about the entropy. And that's what we're working towards. Okay, so let's talk about what that means. So yeah, so as temperature increases, our ability to predict what a molecule is doing decreases. Therefore, the entropy increases. The entropy is a measure of how random a particle is. And as the temperature increases, the particle becomes more random. So again, in a solid structure, very low entropy because we've got a really good idea where those molecules are and what they're doing. In a liquid, as I just showed you there, we know those molecules are somewhere in this jumble. They're moving around a little bit, but they're pretty predictable. It's pretty easy to predict what they're doing and how. So pretty low entropy, but higher than a solid. And if once they get into the gaseous phase or the vapor phase, very unpredictable. So very high entropy. If you compare the entropy of saturated liquid water to saturated vapor water at the same pressure or temperature, you'll notice a very major difference in the entropy. That's because those molecules are moving more unpredictably in the vapor form or in a gaseous form. So a funny thing happens when you reach absolute zero. Absolute zero in theory is when all molecular motion stops. All the molecules, all the atoms stop moving. So if the substance forms a solid, forms a crystalline structure where all the molecules are equally spaced relative to one another, and they stop moving. This is what happens is what we call the third law of thermodynamics. And this is a direct quote from the Chengel and Bowles text that tells us that the entropy of a pure crystalline substance at absolute zero temperature is zero. Once you reach absolute zero, the molecules stop moving, and we know exactly where they are because they're in a solid structure. 100% thermodynamic probability, meaning zero entropy. That is the third law of thermodynamics. Right? And so interesting things happen. In theory, 100% of heat could turn into work if we dump it on a sink that remains at absolute zero, because if it remains at absolute zero, we're not generating any new entropy to add heat to it. That's kind of interesting. Anyway, some really, in just kind of in the interest of time, I'll let you explore that further if you really want to, but some really interesting things happen based on if we can achieve absolute zero and maintain it. Okay. So what does this mean for us? Well, I think I said this early on in Chapter 6. As long as you conserve energy, we could propose all kinds of crazy things. We could propose a spontaneously cooling can of Coke if we didn't have to worry about the second law of thermo. Because the first law just wants to know, was energy created or destroyed? Did you remove as much energy as you lost? That's it. So the first law is not really concerned about the difference between heat and work. The second law, though, is. The second law really doesn't care about how much work you do to the system. The second law really is more concerned with the heat, because the heat is kind of a lower form of energy, and it causes chaos. So if I heat up a system, that increases the chaos or decreases the thermodynamic probability of the system. So, but the work, though, if I apply work, right, to, I'm looking to see if I've got anything here that I could roll. Well, I can take this pen apart. Right? So I can do work to this pen here and get all the molecules kind of moving in an orderly fashion. Right? It works a lot better if I've got a ball bearing or something I can roll. This doesn't want to roll, okay? And it's not rolling very efficiently, okay? But so here's the thing: if I took a fire, like if I took a lighter and I applied heat to this, and we think about what are the molecules doing? Well, if I apply heat, the molecules become much more chaotic. And I'm increasing their energy. But here I'm just applying a little bit of force, and I'm making the molecules move, but they're moving in a predictable, orderly fashion. And that's really the difference between heat and work, is are you making the molecules move more chaotically? That's heat. Are you making the molecules move in an orderly fashion all together? That's work. Right? And that's really the difference. And the second law describes, the first law doesn't care which is which. The second law does. Now the sun's fixing to come in on me here. And let's see, what is this? You can see my reflection now. Let me close my blind. So I've just got a break in the clouds there. Alright, how's that? That's okay. Alright, I apologize there. I'm not exactly in a professional quality studio. Okay, so again, first law cares about energy. Second law cares about entropy. And what does that mean for us? Well, it just kind of depends on what are we doing to the molecules of the system. Okay. So it's really cool when we think about it. It's a lot more in depth than we would need necessarily to solve problems, but it's important we at least talk about it. Okay. Alright, how are we on time? So let's at least set this problem up, and I know you probably can't see it. It is in the PowerPoint slides for you there. Let me pick this up so you can maybe read that a little bit better. I'll read it to you real quick. Steam enters a turbine with a pressure of 30 bars. This is from another text. They like unit bars. Temperature of 40 degrees Celsius. Inlet velocity of 160 meters per second. Saturated vapor at 100 degrees C exits with a velocity of 100 meters per second. At steady state, the turbine, and that's steady flow for us, flowing steadily, the turbine develops work equal to 540 kilojoules per kilogram of steam flowing through the turbine. Heat transfer between the turbine and its surroundings occur at an average outer surface temperature of 350 Kelvin. Determine the rate at which entropy is produced within the turbine per kilogram of steam flowing. Neglect the change of potential energy between the inlet and the exit. Okay, so we can at least set this up, and I can at least show you how to write the first and second laws. And what I'm going to have you do in a little bit is pause the video, write out a first law and second law equation for this, similar to what you would do for the timed questions on the exam. Write out your first and second law, and then let's talk about getting those simplified. So let's talk about our givens here. And you could do that right now. If you wanted to pause, write down your givens, write down your first and second law, or back the video up and read that. Write down your givens, write down the simplified first and second law, and then I'll show you mine, and let's see how we do, okay? So this is T1, 400 degrees C. P1 is 30 bars. We can convert that. And a V1, an inlet velocity of 160 meters per second. It exits as a saturated vapor, so X2 is 1, and they give me T2 is 100 degrees C. Exit speed is 100 meters per second. They've told me to assume Z2 is equal to Z1. And they've also told me little w out. Little w out is 540 kilojoules per kilogram. And they've told me the temperature of the surface. (350 Kelvin). Okay? All right, again, pause it here and go write your first and second laws and simplify them. And then come back and let's see how we do. Okay, you got them? All right, so to write the first law, we're going to draw the turbine. What crosses the boundary? Well, I've got power out, I've got mass, I've got mass. I'm going to do this quickly because I don't have a lot of time on this video. What else crosses the boundary? Heat. They've told us we're losing heat. What do they want to know? They want to find the rate at which energy is being produced. They want you to find Sgen. That's what they're after. So we're going to use the second law to find Sgen. You can start with that if you like. You can say S2 minus S1 is equal to the integral, and if I use little s's here, that's del little q over t plus little Sgen. Okay? What do we know? We know that the surroundings is at a constant temperature of 350 Kelvin, so this actually becomes little s2 minus little s1 is equal to q net in divided by the temperature of the surface plus little Sgen. Okay, so this needs to be my only unknown. I need to be able to find everything else. Well, I think I can find properties. I need to be able to find Q. Now, how can we find an unknown Q value? First law, that's an unknown energy, right? So we use the first law to find that. What does the first law look like? And I'm going to run out of time here. Yeah, we'll write the first law on the next video. Okay, so you're going to hear a pop here.